Hello guys, welcome to another calculus video. Today we're going to be talking about differentials and implicit differentiation. So this is where the word for differentiation comes from. So we're going to actually talk about what are these. And implicit differentiation. So this is another type of differentiation. Currently we've been doing explicit differentiation, which is when you have f of x equals something, and then you differentiate it and you get f prime of x. But today we're going to be looking at more complex examples where instead of having f of x, you have y. And so we'll have something like, I don't know, for example, x squared minus 2xy equals 0. Now, in this case, we can't just solve for y in terms of x because there's a more complex relationship here. So how do we differentiate it? We'll look into that in this video. So first we're going to talk about why use y. So I'm going to first give an example here. Y squared equals x squared. Now in this case, we can just solve for y. So we can do y, we can take the square root, that was a really ugly square root, equals plus or minus x. So if you look at the graph here, we have y equals x, and we have y equals negative x. And as you can see, this does not pass the vertical line test. So y is not a function. But since we're using y instead of f of x, which by definition is a function, we can do some more complex relationships and we can still solve for the slope of the function. So let's look into how we can do that. First, we're going to have to talk about differentials. So we're going to talk about the reason why we use this symbol to talk about differentiation. So first, we're going to talk about delta y and delta x. So delta y over delta x, delta means change. So whenever you see this little triangle, it's a Greek letter and it means the change in. So this means the change in y over the change in x. So we can see the change in y over 2 points is something like y2 minus y1 over x2 minus x1. And so if we want to find the instantaneous rate of change, that's the derivative or the slope of a function at a certain point. For example, at this point, this tangent line represents the slope of the function. We need to move these 2 points close together. We talked about that in a previous video where we derived the definition of the derivative. So as x1 gets really close to x2, delta x goes to 0, delta y also goes to 0. And we come up with new names for delta x and delta y. When delta x gets really close to 0 and delta y gets really close to 0, we call them dx and dy. Now, we can only use dx and dy when we're talking about infinitesimally small values of dx and dy. So if we look at this picture here, this Desmos graph, we have a graph of y equals sine x in the blue. We have the tangent line in the orange at this orange point that you can see. And these green things, these green little lines, this represents delta x and delta y. So it's quite easy to see visually that the slope of the tangent line is equal to delta y over delta x. But in theory, if we take delta x and delta y and we make them really, really small, then they become dx and dy, which means that the slope of the tangent line is just going to be dy over dx. And so this is why we use this symbol here, because if we say d, which is in this case means the change in over dx, the change in x, so that this whole expression means the change in y over the change in x, and so we can rewrite this as dy over dx. So we're going to see how we can solve for dy over dx. It's going to be very similar to solving for f prime of x, except for the fact that now y does not have to be a function. So first we're going to talk about the chain rule review, because this is by far the most important thing we're going to talk about today. So the chain rule states that the derivative of f of g of x equals f prime of g of x times g prime of x. But we're going to say that this also holds true whether or not g of x is a function. So we're going to say that the derivative of f of y with respect to x is f prime of y times dy over dx. And this is how, when we have some equation like y cubed minus 4x squared plus 3 equals 0, we can solve for dy over dx, because every time we differentiate a term that has y in it, a dy over dx is going to pop out because of the chain rule. Okay, so the steps that we're going to use to solve for dy over dx is we're going to differentiate the entire equation. So we have two sides of an equation. We're going to differentiate both sides. Then we're going to rearrange the terms so that dy over dx is on one side. We're going to factor, and then we're going to solve for dy over dx. So let's look into an example. Okay, here we have a pretty simple function, y squared minus x equals 0. We're going to find dy over dx. So remember, our first step is to differentiate. So we're going to differentiate the whole equation. Okay, so how do we find the derivative of y squared? Well, as we talked about before, the derivative of f of y is f prime of y times dy over dx. So in this case, f of x is just going to be x squared because this is y squared. And f prime of x equals 2x. So to differentiate y squared, we're going to use this formula, f prime of y. F prime is 2x, so 2y times dy over dx, as you can see in this formula. And the derivative of negative x is just negative 1, and the derivative of 0 is just 0. Okay, now our next step is to rearrange the terms so that dy over dx is alone on one side. So we're going to keep this term on this side, and we're going to add 1 to both sides. Then finally, to solve for dy over dx, we're just going to divide by 2y. So dy over dx in this equation is 1 over 2y. Now I know you're thinking, this is kind of weird. Usually when we solve for a derivative, we have an expression in terms of x. But since y isn't necessarily a function of x, there can actually be multiple values of y for x. So we're going to leave y in here because, well, I'll show you an example later. But in general, the derivative of y can be a function of x and y, not just a function of x. Okay, here's a more complex example. Let's start. So first, we have to differentiate both sides. So this we did before. This is 2y times dy over dx. And now we're going to talk about this. So this is going to be negative 2 times the derivative of xy. How are we going to do the derivative of xy? Well, we're going to use the product rule. So the product rule says that the derivative of f of x, g of x, is f prime g plus g prime f. And we're just going to, instead of using f of x and g of x, we're going to use x and y. So the derivative of x is 1 times just y, plus the derivative of y is dy over dx times just x. And the derivative of 0 is 0. Now we're going to multiply all this out. Now we're going to just move all the terms that don't have dy over dx over to this side. And I'm also going to go ahead and factor it just to make this quicker. So on the left side, we're going to have 2y minus 2x dy over dx. And we're going to move 2y over to the right side. Okay, now we just need to divide by this, and we'll have dy over dx. So dy over dx equals 2y over 2y minus 2x. And we can cancel all these 2's. So this is just going to be y over y minus x. And that's our answer. All right, we have 2 more examples to look at. So now we have a little bit more complex of a function. We have sine of xy equals 1. We need to find dy over dx. So let's differentiate the whole function on both sides. Okay, so this is going to be cosine of xy times the derivative of xy, which we did last time. We just used the product rule. 1 times y plus dy over dx times x equals 0. Okay, now we're going to multiply this out. Okay, now we just need to move this term to the right side and and then divide by that term. So I'm going to do that real quick. Cosine xy dy over dx equals negative y cosine of xy. Okay, Now, right now I see that actually we have cosine of xy on both sides, so we're going to go ahead and cancel this. And obviously normally it's not good to cancel things just right away, but when we're talking about derivatives, it's generally okay. And then we just need to divide by x on both sides, so our derivative is going to be negative y over x. That's our answer. All right, last example. Now this is the equation for a circle. We have x squared plus y squared equals 1. This is a circle with radius 1 centered at the origin. We're just going to solve for dy over dx. So the derivative of x squared is 2x. The derivative of y squared is 2y dy over dx. And the derivative of 1 is 0. Okay, we're going to now move everything that doesn't have dy over dx over to the right. And now we're going to divide by 2y. We're going to cancel these 2's, and we're going to have negative x over y. Now, for the other examples, it's been a little bit complicated to think about, but I'm going to show you a way that we can kind of understand what does dy over dx equals negative x over y even mean anyways. So, as we said before, dy over dx equals negative x over y. And here's our equation. So x squared plus y squared equals 1 gives you a graph that looks like this. So as we said, dy over dx equals the slope of a function at a point. So we're going to just choose a point on the circle. Let's choose this point right here, which is 0, 1. So now we're going to evaluate dy over dx at this point and see if it matches up with the slope of this function. So when x equals 0 and y equals 1, negative x over y equals 0, negative 0 over 1 equals 0. And if we look at the tangent line at this point, that appears to match. I know I'm terrible at drawing lines, but you can see that that does line up, and that does give us the correct answer because the slope of this line is 0, and that's also what our dy over dx gave us. Now let's look at another example. Let's look at this point right here, which is square root of 2 over 2, square root of 2 over 2. So let's plug in negative x over y. So it's just going to be negative 1. And if we look at the tangent line here, the slope is also negative 1. So that's another example that works just fine. But I know you're thinking, well, why couldn't we just solve for y and differentiate normally? Well, if we did that, then we would have to say that y is a function of x, which means we would have to cut down. This entire bottom half of the circle wouldn't be allowed because we have to have a function, which means it has to pass the vertical line test. So I'm going to show you that it actually works no matter where you choose your y point. It doesn't have to be on the top half. If we choose this, which is square root 2 over 2, negative square root 2 over 2, and we plug it into negative x over y, that's going to be equal to 1. If you look at the tangent line, it's also going to match. That slope is about equal to 1. So that's just proof to you that no matter where you choose to your point in xy, as long as it's actually on the graph, it will equal the slope at that point. And so that's why implicit differentiation is so useful, because with implicit differentiation, you can take some relationship like this, where y is not necessarily a function of x, and you can still find the slope of the function. So that's why we need to know implicit differentiation. Anyway, I hope you found this video helpful, and I'll see you in the next one. Make sure to do some practice problems by yourself because that's very helpful. And as always, keep learning.